Yeah, so hi and good afternoon, everyone. So this is the third lecture in the mini school series on parallel computation with GPUs and introduction to programming with CUDA. The format of today's lecture will be the same as the previous week. So our speaker today, so Prof. Japie Greeff, will be giving a 45-minute to 1 hour lecture, and then we'll have time for answering questions at the end. So if you have any questions throughout the talk, then please feel free to type these into the Q&A facility in Zoom, and then we will get around to answering these at the end of the lecture. Unless there's any other further points, then let me hand over to Prof. Japie Greeff. So thank you.
So this one is Prof. Martin. I'm doing the next week's one.
Yeah. Oh, sorry. Sorry,
No
I got confused. So okay. Apologies. So Prof. Martin Bucher will be giving today's lecture. Okay, thanks.
Okay, let me see. Let me share my screen and let's see. Let's see, how do I do this? Okay, let's see. First of all, a few practical announcements. So we would like to apologize when we, advertise this course. We told you that we were going to provide people with accounts and but that this would be hands-on, and that's still our intention. We're having some difficulties, and we don't know whether we need another different Linux kernel in order to, get the machine that we were going to use to work, or perhaps the GPU card is broken. But we're working on this, and we will provide this to you. I mean, hopefully within the next week we can solve this problem. The other announcement, and maybe Japie can put this on the chat, but we have well, so far the slides for the first 3 lectures on this Dropbox. And if you go to the past events on the NITheCS webpage, there's a link for resources, so you can access those. And we intend to put some more materials on, in particular, programs and sort of instructions on, how to use this machine once it becomes available. So our apologies. We're working on this, and we really hope to get this solved in the next week or so. And then you can play with some of the programs and do some experimenting yourselves, and we'll make ourselves available. So as to the lecture proper today, I'm going to continue on what Japie was talking about last time. And we're actually going to look at an example where the GPU does much, much better than a CPU. And I mean, this is a bit academic in that if you were really doing linear algebra with a GPU, you probably wouldn't want to program it yourself like we do here, but you would want to use a library like CU Blast, yeah, and which would be hard to beat. But the purpose of this course is somewhat theoretical, that we want to, give you sort of a toolbox of parallelization tools in CUDA, and sort of illustrate things in a simple context. And we also want to, make you aware of what you have to look at for performance. So matrix multiplication and reduction are going to be the two examples. And I'll just go over very quickly, and the slides serve more as a reference. So I'll go rather fast, but you can over some of these things, but you can, look at the slides and look at the code, and, it'll be much easier to read. And we're also going to talk about performance. So Japie talked a lot about the architecture and emphasized how it's different from your CPU architecture. And we're going to look at how that impacts on performance. I'll just start with timing, because we're going to time our programs. And this little diagram shows you a little about, how the, oops, this is, I mislabeled that. This shouldn't be kernel, but host. The CPU and the device. And basically, they're independent units that, operate in parallel, and they're connected by a bus, which is not particularly fast, not that slow either. So if you want to time a kernel, which is on the device, you need to use special commands that do timing on the device rather than the usual CPU timing commands. So so if we were timing, parts of a program rather than a whole program, in the C++, there are these library functions, and in C, they're included in the header file time.h. And the same thing is called ctime in C++. So you can use either of these. And just in general, for people who haven't done a lot of C programming, the C standard library has lots of stuff, and you really only need to be aware of what there exists. And you can go to, lots of places and look at these header files, and then there's a description of what the functions are, what the arguments are, and, you just look it up, and rather than try to memorize. So this is from this C++.com. We have for the time library, there are these different functions, and they're helper functions, but the two main ones are clock and time. And time gets, the real time, the wall clock time, and clock is looks at your particular CPU. So if you're working on a system where you share with other people, it's the, number of CPU cycles devoted to your process. And then we can click on this, and, we're told that what the program does, and you see a lot of types that are clock T. Clock type would be some sort of an integer. I don't know exactly what. And then the other thing you pick up is, the number of ticks per second. So you can use these to time part of a program. And let's see. Let me hide this bar. Okay, then if we want to time stuff on the device or time a kernel, we use these CUDA events where we have to define them, and then this creates some sort of a structure. And you can see here we're timing this operation saxp, which is a kernel call. So we create this event before and after, and then we have to synchronize, and then this is all code, in the host function. And then we get in milliseconds the time between these two events. So that this is what you would use to time your kernel. So we're going to do this for the matrix multiplication to see how much better we do than doing the operation on the CPU. So let's see. So the issue of optimizing matrix multiplication. So I'm just going to show two programs, and I'm not really going to look in a lot of detail at all the optimizations. But if you're interested in this blog of Simon Berm, he has a really extensive discussion, and there's actually quite a bit to learn. And he uses sort of as a goal to do as well as the library that is provided by NVIDIA. So this is BLAS, basic linear algebra subroutines. So basically, this is in the 70s. People would, for each computer, write these special libraries, often in assembly code, that would be really fast and, use the particularities of the machine. So that these are the things that are actually used. And there's also at the bottom of the page, the CU BLAS, which is the NVIDIA. So that's sort of the goal. But as I said, this is an academic exercise, because if you were doing for your research linear algebra, you would just use this CU BLAS library and install it and not try to write your own code. So this is from the Simon Berm website, where he has, well, I guess it's 10 different realizations of matrix multiplication, and he compares the speed, 1 over the time, to the CU BLAS, the NVIDIA proprietary library. And if you just code in the most naive way, you don't do very well. You get 1.3% of the speed, and then he has various optimizations. So I'm going to show you in the naive implementation in the 2D block tiling. And I don't get, I mean, the numbers are different, but it's going to depend on the size of your matrix and the exact GPU card that you're using. So this is a very nice blog where he explains in great detail. Okay, so let's look at the sort of naive implementation. So in this code here, we have, so this is in the same spirit as Japie's vector addition code, but there's a lot more going on than just adding to numbers. So for the vector addition, I mean, you really wouldn't do very well. I don't think you would do better in terms of a performance for, compared to a CPU, because you need to transfer the numbers, the vector, from the CPU to the GPU, and then you do your algebra, and then you move it back, and there are lots of overheads. But basically, the idea here is for each index, so row column indices in the final matrix, there's one thread per matrix component. And here there's an if statement because you might need more, the way you divide up into threads and blocks, there can be edges. But basically, this is just, naively coded. And the reason it doesn't do that well is that there's a lot of memory accesses, a lot more than you really need. So it's basically slowed down. Well, you have all these processors that are very fast, but they just sit around and wait to be able to access the global memory. And the other number to take away is that there is a latency of something like up to 100 clock cycles for accessing global memory. So that's basically, in a nutshell, why you just get 1.7% of the, best performance with this setup. Okay. Let's see. So this is the code, and I'll just highlight a few things. So there are these grids that well, a grid of blocks, and then an array of threads within each block. So each block runs on a separate streaming processor, which, as Japie explained to you, gives out instructions to all of the threads. So here we take 32 times 32 threads in a block. And you can have an arrays up to 3 dimensions. So we've set this the third dimension equal to 1, and this is like a 3-dimensional vector. Okay, so a lot of this mirrors what Japie explained to you for vector addition. You know, we start by allocating memory on the CPU on the host, and here we have error checking, and then we use a random number generator to create some input data. And then these commands have been wrapped in this error checking code. So the error check doesn't do anything except it'll stop your program with an error and tell you what line you're on if something went wrong. So this is important because otherwise you'll just spend a lot of time trying to figure out what went wrong. We copy the data. So this is on the GPU, we allot the memory, we copy it. So that's through this, you know, PCI bus. Okay. Then here this is code you saw before with the error checking. I mean, with the timing, the event create. And then we launch this matmul matrix multiplication naive kernel. And then we check the error code, and then we do the timing, and we print out the timing. And then we copy the data back, and everything has been wrapped in this error checking routine. And then we do the same thing with the host function. So we do the matrix multiplication on the CPU, and we print out the timing, we compute the speed up factor, how much faster is the GPU compared to the CPU, and then we compare the results and, you know, see whether the calculations agree. So it's all rather simple. You know, this is just a simple program to illustrate the concept. Okay, the other thing, let's see, where is the other thing we do is we do this tiling. So I'll go back, but we can break this matrix up into sort of bite-sized morsels. So if we just use our naive program, we're doing order n cubed, I guess 2n cubed, fetching the matrices from memory. So we're rather than reusing elements, we're creating all this memory traffic. And if we break the matrix multiplication up into these tiles, then if we can put all of the data in shared memory or in registers or whatever that are much faster, then we don't have this memory bandwidth problem. So that's what we sort of implement here. So let's see. Okay, the tiled kernel. So the first naive kernel just like the vector addition, there's no need for synchronization. Each element in the matrix product can be calculated independently of the other one. But here the idea is in this, these two lines, we have 32 times 32 squared threads, so 1,024 threads, and that's the size of these blocks. And each thread reads in an element. So that reduces the traffic by a large factor. And then in taking this partial sum, most of the data comes from something that is read in from other threads in the block or the tile. So that means that all the data has to be read in before anyone makes a calculation. So we need to synchronize in these two steps here. And then this outer sum is, over the blocks. So if we've, divided by the dimension of the grid, I mean, that's the number of pairs that we need to sum over. So there's this outer loop, and then the sum gets written. So basically, each block in the grid does a separate block in this, block representation of the larger matrix. So they can run independently of each other, but the thread needs to be synchronized. So the whole idea is to reduce the memory traffic. And then we can look at the results. So here we have a grid of blocks. So this is 64 by 64. So that would be, I think, 4,098 blocks. And then each block is 32 by 32. So this is 2,048 times 2,048 matrix. So that's the size of the problem. And if we use the naive implementation on CUDA, we get 83 milliseconds. And then we compare that with the host. So that's the CP calculation, and that takes 12 seconds, rather than less than a tenth of a second. So here we have seen a speed up of 141, and the calculations agree. So you can see that the GPU is doing a lot better. And then when we look at the tiled example, everything is the same, but we get a factor of 3 speed up, and the total speed up factor is about 350. So I don't know if these are really fair numbers, because these are simple programs, and I haven't really made any attempt to optimize anything, but it sort of gives you a feeling for things. And let's see, I mean, this is somewhere where you really need to think about the hardware a lot more than you do when you program on a CPU, because a lot of things on a CPU program just happen by themselves. There's this hierarchy of caches, and things are automatically taken care of. But we can analyze the matrix multiplication calculation in terms of what is the best that we could hope to do. So you can look up for each individual GPU chip, what is the maximum memory bandwidth. So this is between the GPU cores and the global memory. And then the other figure is how many floating point operations can you do, or what is the maximum. So the latter is basically, well, we have thousands of cores, and if we can keep them all busy so that they're just doing floating point operations, how many flops would we get? So if you look at this problem, it's reading in things from the global memory, which sort of feed the cores, and then doing calculations, and then writing less out. So you can ask, is the problem memory bandwidth, or is the problem the computation? And if we would find that the memory bandwidth is is not saturated, but the computations, then there's very little motivation to think about clever things with keeping things in registers and not reading stuff out from global memory. That's just sort of a waste of time, or it'll maybe give you a few percent improvement in performance. So if a program is limited by the traffic to global memory, then it's called memory bound, and the other extreme is computation bound. And the ratio of these two rates in your program, and also compared to what the GPU can do, sort of gives you an idea of where to look for optimizations. So this is maybe not Japie and I have been using different GPUs, and the one on the machine we want you to use is yet different. It's a more recent one, but this is a spec sheet that I got from the Hopper architecture. So this is really more recent. And let's just go through some of these things in this table. So the columns are different different GPUs, and here we have floating point 32, floating point 62. So let's look at the floating point 32. So we got 67 teraflops. And then let's go to the GPU memory bandwidth. And we can read out that this is 3.3 terabytes per second. And perhaps the other thing to look at on this table is the last the last row gives you the capacity of the channel between the CPU and the GPU. So you can see that that's much slower. So these are just approximate figures because we have caches and things like that. And, you know, that's not really taken into account. But the idea is here to just look at order of magnitude performance. So let me go and try to exploit some of these numbers in this table. And so we take this would be a float, not a double precision. So we get 67 teraflops, and then we can divide it by the memory bandwidth, which is 3.3. So if the two are both saturated, we're going to have 20 floating point operations per byte that is transferred. So in the next line, I sort of explained to you something in the machine instructions. So this isn't C, that when you're doing something like a sum over a row and column, you can do this operation every clock cycle. So this counts as one sort of unified floating point operation. Then we look at, well, there are two inputs for which are each 4 bytes long. So we get 8 bytes transferred for each one of these floating point operations. So we see that this ratio on top is an 1/8 rather than 20. So we would have to reduce the memory traffic by a factor of 160 in order to be sort of computation bound, or just where the memory throughput and the computation throughput are the same. And you can see that if you read in, so if we do the naive implementation and there aren't any caches that are helping you out, then you know, you need to do n cubed reads from memory, you know, whereas the minimum would be n squared. So there's sort of a factor of n you can play with. So this is why the tiling is a good idea. And I mean, here I work some of this out, how much time you save. And well, I've explained most of the points, but the choice of the 32 by 32 tiles. So you could ask, oh, well, why not make them even bigger? Is that there's not a lot of shared memory. So the point is that if each thread is reading in stuff from its shared memory, you know, the shared memory decor bandwidth can be much higher. So this sort of gives you an idea of what to look for and how to optimize and, understanding your performance. But of course, there are things that are hard to predict from first principles. So we don't know with the global memory, the role of the caches, and that depends a lot on the data. So you have to do a lot of experimentation and optimization. And that's nicely explained in the blog that I cited, where he goes through this stuff in a rather careful way. Okay, so before I talk about reduction, I want to explain to you another limitation of the GPUs. So as Japie explained to you last time, that each core, which has its registers, and it has its own data and its own arithmetic units, which do addition, multiplication, and all of that. They don't have their own instruction stream, but they get all their instructions from a common source, which is, the streaming multiprocessor for that thread. And well, actually, for a warp for 32 threads. And let's look at code like this, where you have some sort of a condition, and if it's true, you do one thing, and if it's false, you do another thing. So if we had independent CPUs, then some would take this branch, the true branch, and others would take the false branch. But what happens in a GPU is that it'll first test this condition. Then for those processors, if the condition is false for all of the processors in a warp, then it'll go to the else. But if it's true for some of them, the others will be told, well, just wait, don't do anything. And then a fraction of the processors will execute this first code and another the second code. So this is one of the drawbacks, or one of the trade-offs. Well, you can save transistors by not having independent instruction caches. And if you read the documentation in more detail in the early versions of CUDA or the older GPUs, you could actually run into a lot of trouble, because if something needed to be calculated in this first block that relied on another thread doing the else, well, it would just be waiting forever, and then you get a deadlock and your program will freeze. So this is one of the pitfalls of parallel programming that Japie will discuss in the last lecture. And another example is that if we have this an infinite loop that will break if it just keeps on trying till a condition is satisfied. Well, in order for the other processors to get to the out of the loop all of them have to get out. So this is an inherent limitation, or one of the trade-offs. So, you have a fixed number of transistors, and you can either have individual processors that have more capabilities, or you can share this instruction stream. Okay, the last thing I want to talk about is an intrinsically parallel algorithm. So basically, this is the parallel computation of a large sum. So say we want to add up 1,000,000 elements. Well, in a CPU program, it would take 1,000,000 steps, or that's the time. So we would write a for loop, and we would go through sequentially. So the question here is that if you have lots and lots of processors, and in theoretical computer science, we could say, well, we have an infinite number of cores, and we just care what is the overall time. So with associativity, we can regroup our operations, and we can do this a lot faster. So we can sum these 8 elements in 3 steps. So you see this tree that if you follow it sort of backwards in time, it just bifurcates several times, and then you see the time is equal to log 2 of n, and then this symbol here is the ceiling. You round it up to the next higher integer. So this is a common parallel algorithm, and there are other operations where this works. If you want to know, has some condition been met, and a million different threads, you can combine with the logical OR, and you would use this kind of reduction. Or if is there any where it hasn't been met, with the and, etc. So a binary operator that's associative will be amenable to the same algorithm. So we can sort of diagram this in terms of, we have numbers, and the 0 to 7 could be array indices. And here we're going to write an implementation that basically overwrites this vector that could be in global memory. And you see the arrow means you just added the contents of one to the other. So you can see here in 3 steps, we get our final sum. And of course, this will, save a lot more time with 1,000,000 than it would adding together 7 numbers. It's not really, it doesn't really help that much. So let's see. Here is the kernel code that does what was described in the previous slide diagrammatically. So we have the array, and then the size of the array, and then the final sum. that gets returned. And this gets overwritten. So, I've just programmed this out. And as you can see, there's we need a synchronization because this all of these arrows need to be done before you can go to the next step. So you have to think about synchronization rather carefully in order to write these algorithms correctly. And here's some code without error checking. So this is bad practice, but it displays easier, more easily, and here you can see the result, that the sum of this test case is the same as if you just do it on a CPU. And I haven't timed this. So I think I will stop here. Japie will continue on for the next lecture with some more parallel algorithms and some more features. So by the end of this course, you should have seen most, not all of the sort of parallel functionality that is, added above and beyond C++. So these are sort of the building blocks for putting together and realizing parallel algorithms on a GPU. So thank you for your attention. And yeah, maybe we can take some questions now if there are any.
I think we've managed to answer all the questions in the time that they happened. I think the one question maybe just to you, Graham, is just around certificates of attendance. I'm not aware of NITheCS offering those on mini schools, but that was one I wasn't sure about.
Yeah, so as far as I'm aware, NITheCS don't offer certificates of attendance, but I can inquire about that.
Great.
So hopefully by next week I can deliver an answer. But yeah, as far as I'm aware, I don't think that there are certificates of attendance, to my knowledge.
Great, thanks.
Are there any additional questions?
Seems not.
Okay, so we will continue next week with the final lecture by Japie. So thank you for your attention.
Yeah, thank you, Prof. Martin Buchner, for that nice lecture. So yes, hopefully see you all again next week for the final lecture.